Well, guys, we're hitting the final section of Chapter 4, so 4.6. We're going to look a little deeper at isosceles triangles and equilateral triangles. So remember we talked about this early on in the chapter. Isosceles are cases where two of the sides are congruent, and really the formal definition of that says if at least two of the sides are congruent, then it's isosceles. If we can show that all three sides of a triangle are congruent, then we call it equilateral. So equilateral is really more of a specific type of an isosceles triangle if we look at it that way. So here's kind of the main idea on this one. If we have two sides of a triangle that are congruent, then the angles opposite of those sides, which we call base angles, are also congruent. So here's what this is saying, and really important, guys, if you're taking your own notes, you need to write this information down. So you really need to write down all of this, because this is kind of the highlight of what we are looking at right now. So if two sides of a triangle are congruent, making it isosceles, then the two angles opposite of those, which would be this one and this one, are also congruent. So we generally call this the base angles theorem. Base angles theorem, right? So base angles theorem says if two sides are congruent, then the angles across from those are also congruent. Guys, the opposite of that, or the converse of that, is also true. If I know that angle A is congruent to angle C, then these two sides must be congruent. The one other thing that they throw into this is the vertex angle. The vertex angle would be this guy. The vertex angle is the one that is in between the two congruent sides, right? So here's the way we always want to kind of look at these. So if I have two congruent segments, the angle between them is the vertex angle. The angles across from them are your base angles. So really important that we get that idea separated out. In fact, let me do this, and I would encourage you to throw this into your notes for reference. So let's actually throw in some vocab here. So if I have congruent sides, those would be those guys right there. They call those the legs. I'm a little hesitant to use that idea because usually that's something we refer to when we have a right triangle. We call the two sides that form the right angle the two legs. So that I don't want that to get confusing with this idea, but that's what they're identifying this as, even though it's not a right triangle. So they're calling those the two legs. The angle between them is our vertex angle. And the angles across from them are called our base angles. All right. So that's what we're getting out of this. So a little more algebra in this section as we're kind of doing some solving, as you guys are seeing on this. So on this one, they told us in the given information that BC is congruent to AB. So they said that this side is congruent to this side. So what we just saw in our base angles theorem is if these two sides are congruent, then the angles across from them are also congruent. So angle C is congruent to angle A. So that's what they're telling us right here. They're calling this the isosceles triangle theorem. In other books, they call it the base angles theorem. I hate when they throw in multiple names for the same idea, because I know that looks confusing. Since this book is calling it the isosceles triangle theorem, that's the one I will try to use as well. So isosceles triangle theorem. So again, that helps us set up the equation that the information for angle A is congruent to the information for angle C. We go on to solve a nice simple equation from there. Guys, as always, make sure you read careful. This one did just say find x, so we can stop here. We don't need to plug it back in. All right, so here now we're seeing the use of the converse of the isosceles triangle theorem. So if you look at the converse of the isosceles triangle theorem, it says if you know that the base angles are congruent, then the sides across from those must also be congruent. So 3x minus 13 must equal 2x. That is the converse of the isosceles triangle theorem. So our setup is right here, a nice easy solve for x. Let's give some of those a try. Guys, again, if you are taking your own notes, you do need to write down these two examples, as well as the ones that we go through down below. So here we go. So just looking to set up an equation to solve for x. We don't have to plug it back in. That's not what they're asking for on this, but read careful because some will ask you to plug it back in and define the length of a side or the degree of an angle. So read careful when you're doing these type of problems. As I look at number 1. So this one I like because it's making us think outside the box a little bit beyond the examples that we just had. So here is my two congruent sides. So if those two sides are congruent, where are the base angles that would also have to be congruent? Well, that would be this guy and this guy, right? So these two must be congruent. So if that's 2x, then this also has to be 2x by our isosceles triangle theorem. So how do I set up an equation for this? So we looked at the beginning of this chapter at something called the triangle sum theorem, which just says that when you look at any triangle, what do we know about all three angles of any triangle? They always add up to 180 degrees. So that must mean that the 40 plus the 2x plus the 2x must all add up to 180. And there's the setup of our equation. Guys, when we're doing these problems, there's two different math ideas going on here. There's the geometry and there's the algebra. Getting this set up is your geometry, right? I have to use geometry properties in order to identify the setup of my equation. And so we already did the geometry. The rest of this will be the algebra, right, that we use to solve it. And so in some of these, just in the interest of time, I might just do the geometry part, which is setting up the equation, assuming that you guys can solve from here with your algebra skills. Let me do this one with you. So if I combine like terms, I have 40 plus 4x equals 180. So of course we would subtract the 40 from both sides. Divide by 4. And that gives us our value for x. So the rest of that would be the algebra, again, on some of these. And of course, guys, in homework, I want you to do all of it. But just in the notes, in the interest of time, I'm just going to help you get through all the setups of these. The rest is just basic algebra when you solve for x. So let's go on to number 2. How would we set up this equation? So according to the converse of the isosceles triangle theorem, if these two angles are congruent, that means these two sides would have to be congruent. So I know that 2x plus 6 is equal to 3x minus 6. And so that was the geometry part of it. The rest of it would be your algebra skills, and I know you guys can solve it from there. So let's take a look at number 3 here. How could we set up an equation for this one? This will look a little more like number 1 did. So here are the two sides that I know, which must mean that angle y is congruent to angle z. That's the isosceles triangle theorem. So if that's 3x, then this must also be 3x. And again, I know that all three angles of a triangle add to 180. They're telling me by that little mark that this is 90 degrees. All right, so let's put all that together. I know that my three angles, which are 3x, 3x, and 90, must all add to 180 degrees. So there's the geometry in our setup. Guys, there is a shortcut in there, and I mentioned this in an earlier lesson, and let me just throw it out there, because we're going to be doing this when we're going to hit a whole chapter on nothing but right triangles down the road. So here's an idea that will help you down the road. I know this adds to 180. If this is 90, what does that leave you with for the two acute angles? Well, if that's 90, these guys must be the other 90 degrees of this triangle in order for all of this to add up to 180. So as soon as I see that this is a right angle, I immediately know that these two angles also add to 90. So oftentimes I'll kind of take that shortcut and I'll say 3x plus 3x equals 90 and save myself a step. if you subtract this over, you'll see that you'll get to that same line of information. It just takes you an extra step to do it. All right, let's go down to number 4. So real similar to the one that we just did. Again, if these two sides are congruent, that means these two angles are congruent. So if that is 6x plus 6, then so is that. And I know that all 3 of these add to 180. So I have angle A, which is 6x plus 6, plus angle C, which we also know is 6x plus 6 by the isosceles triangle theorem, plus angle B, which is 2x. They must all add to 180. So there would be our setup, and then you have a pretty simple solve for x using those algebra skills. All right, here's another one like number 3 was. So again, guys, if this is 5x, then so is this by the isosceles triangle theorem. I know that all 3 of these add to 180. So 5x plus 90 equals 180. And if you want to start there, that's fine. But remember, there is kind of a shortcut to this. I could have said that 5x plus 5x equals 90 as my first line, knowing the shortcut that we talked about up above. Even if you did not start here, that's okay. You're going to subtract 90, and you're going to get to this line as your next line. Let's go to one more of these so I can get to the back side. Again, if this is x, then so is this, because of the isosceles triangle theorem. All 3 of those, x plus 3x, would have to add up to 180. So there's the geometry side of it. The rest will be your algebra skills. All right, let's take a look at this one right here. So, super important box of information that you want to write down if you are writing down your own notes. If you have my notes, I would highlight this box. So a triangle is equilateral if and only if it's equiangular as well. So in other words, if all of the sides are the same, then all of the angles are the same. And this is something we've talked about before. If all of the angles are the same, they have to all each be 60 degrees each. Right? So 60, 60, 60, which of course would add to 180. So in this one right here, they're wanting us to prove that this triangle was equiangular. We're not going to go through this proof. This is more of a proof to support this information, but this is not something we would have to do within a proof. Okay, and so we're going to jump over this one, and let's get down to the algebra skills as well as the proof at the end, which is going to be very important that I want you guys to see. So make sure you finish this one all the way through. So here's what we just talked about. You see those markings. It is telling me that this is equilateral. All 3 sides are equal. Well, again, if all 3 sides are equal, then all 3 angles are equal. So if this and this and this are equal, what would each one have to be in order for them to all add to 180? Well, each one would have to be 60, right? Because 60 plus 60 plus 60 equals 180. So we're putting kind of a few ideas together when we see that, but when I see these markings, I want to recognize, hey, that angle has to be 60 degrees since this is an equilateral and equiangular triangle. Some simple algebra from there. We have our x. So again, guys, when I look at this one, this is equiangular, then it's also equilateral, which means all my sides are equal. So I can just pick any 2 sides, like this one and this one, and say that they're equal. All right, and then of course you could solve for x from there. See one more on here. Again, guys, I see this angle and this angle and this angle are all equal, which means they all have to each be 60 degrees. So there's our setup. That's the geometry. The rest is algebra. Let me take you to the final proof that I'm going to need to teach you guys. But there's something in here extra that I really want you guys to see. if I look at this proof, and let me get rid of this, it's kind of in my way. So let's take the process that we always take. Let me just start out with the given, and I'll show you where this is going to go from there. So our given is simply that angle 1 is congruent to angle 2. So far, within this chapter, all the proofs have been geared toward one idea. And that idea is that triangles are congruent. But that's not the only thing we can do with this information. Right? So as I look at this one, they are not asking me to prove that two triangles are congruent. I don't even have two triangles. What they're asking us to do is prove that side AB is congruent to side CB. Right? So I want to come up with this segment being congruent to this segment. So that's our goal. So as always, let's mark our given information that angle 1 is congruent to angle 2. So that would be him and him. So what else can we do? There's really nothing more I can do with the given. So let's go to our diagram. So what do you guys see in our diagram? We have a very popular idea right here that says vertical angles are congruent. So I can say that angle 2 is congruent to angle 3 by my vertical angles theorem. So if I just said that 2 is congruent to 3, well, take a look at those markings. Something should stand out to you now. What do we now know about angles 1 and 3? Right, look at these two statements. Here's been one of the most popular ideas that we've talked about all year. If 1 is congruent to 2 and 2 is congruent to 3, what do we have to know about angle 1 and angle 3? Well, those guys would also have to be congruent by the, hopefully you said transitive property. Guys, remember that is not substitution. Substitution is only supposed to get used with an equal statement, not a congruent statement. Okay, so this does need to be transitive property. But now that we've said that, well, if angle 1 is congruent to angle 3, what do we now know about side AB and side CB? What would have to now tell us that those two sides are congruent? Well, if these two base angles are congruent, that would make side AB congruent to side CB by the isosceles triangle theorem. This would actually be the converse of the theorem. So the original theorem, if you back up a page in your notes, the original theorem says if those two sides are congruent, then those two angles are congruent, right? The converse of that says if these two angles are congruent, which is what we have, then these two sides are congruent, and that's what we're trying to prove. So this would actually be the converse of the isosceles triangle theorem. So we're definitely going to be working on proofs together as much as possible, but hopefully you've gone through these notes and have all these examples for you. But that's going to do it for us for chapter 4.